Okay, so let's get started on the final session. Is this a final session? Final session for today. This was supposed to be shared by Rourke Horstmeyer. Some of you may note that I'm not Rourke. My name is Andreas Felten. I'm standing in for him. Our first presentation is by Aswin Sankaranarayanan, and he's a professor at Carnegie Mellon University. And the presentation is titled PlatonicVR.
Thank you, Andreas. So, over the last many years, my group has been working on near-eye displays, largely looking at how to improve various aspects of various capabilities that such displays can have, concentrating more or less on improving depth perception. Looking at these demos and the kind of results we're putting out, there's a sinking feeling that field of view matters a lot more in terms of producing impressive results, or in general, that seems to be the thing I cared about more than anything else. So this led to this thought experiment in building wide field of view near-eye displays, and this particular result that we call PlatonicVR. So this is joint work with my PhD students, Sagnik Ghosh, who's in the audience today, as well as Anat Levin from Technion, and other collaborators from Carnegie Mellon, Edward, and Anthony Rowe. So a good place to start is to sort of scope out what the human eye can do, right? So in terms of field of view, it's a rather impressive instrument. It's capable of seeing more than 90 degrees towards the temple and about 60 degrees towards the nose and about 130 degrees vertically, right? So, this is extremely impressive when it comes to the underlying specification in terms of the range of angles that it can image it for any fixed head location. Now, another sort of feature of this, and something that we sort of saw earlier in the keynote today, is that the eye also has a foveated sensor. So in that the resolution of imagery that it senses on the retina is very high in one particular region called the fovea, and the resolution progressively goes away as we look at as we go away from this particular fovea. So for instance, on the fovea we get the resolving power is extremely high, upwards of 48 cycles per degree, but even a few degrees of the fovea, if you look at an angle of a point on the retina that's even, let's say, 5 degrees, the resolving power of the eye plummets by order of magnitude, right? So which means at any particular instance, if I'm looking at someone, say Gordon, right, I'm seeing Gordon at very high resolution, but the rest of you are all resolved very poor, this thing. So naturally this begs to ask the question, I have this very large field of view in front of me. How do I see it in all of its complexity, in all of its detail? So the answer to this is, of course, something we all know very well, right? This is something we do by rolling our eyes, right? So by changing the point where the fovea is within the field of view, and by doing this, by essentially rotating the eyeball, we can explore this visual field in front of us, this very large field of view that the eye can actually see. Right? Again, this is something we live with our eyes, so this is something we're all used to, we do it intuitively, right? But computational near-eye display, or basically any 3D display that you want to build, has to satisfy all of these properties, has to accommodate all of these features of the human eye. And what this means is that it obviously has to support a very large field of view, right? The kind of numbers I specified earlier. But perhaps more interestingly, that it also needs to support an eye box that grows proportionally to the field of view, right? So imagine I have some display with some particular field of view. If I want to build a better display with a larger field of view, it's not that the eye box, the region where the content is produced faithfully, can remain the same. The content has to grow linearly with the eyeball. So for example, the human eye, most of us can do plus minus 50 degrees of rotational motion with our eyeball, and given certain diameters of the human eye, you can come up with this number that to satisfy the full rotational motion of the human eye, you need to have an eye box that's nearly an inch along each of the axes, right? So as a design problem, this is extremely challenging, right? Not only are we asking for a very large field of view, we also need the imagery to be produced faithfully over a large region in which the eye can move, right? So that's because of the rotational motion of the eye. Now, thankfully, there is some interesting features of the eye that we can exploit to make the problem simpler. And one of them is the foveated nature of the eye. So despite having to resolve this huge cone of light over this huge area, only the foveal light rays are actually do need to be resolved at the highest resolution. As we go away from the fovea, for light rays that are resolved off the foveal region, what's generally called the parafoveal region, we can resolve these at poorer resolution, take a hit in performance, and hopefully, if you can exploit it carefully, we can build systems that can that are not computationally as challenging to design. So that's the premise of this particular work, and hopefully by the end of the talk I'll show you a design that hits some of these features. Now before I get into the specifics of what we did, let me briefly talk about some of the broad approaches that we can use in current literature to satisfy this particular problem. So one approach is to not use optics at all, right? And this particular approach, it's a very nice line of work, starting with this work called pin light displays. And what they do here is they divert light through pinholes effectively. And because you're running through pinholes, you don't have to worry about focusing and defocus effects with lenses and things of that form. And then modulate the light with an LCOS or some spatial light modulator. And now you can produce content. And in principle, if you could do it over a large field of view around the eye, you could satisfy the field of view requirements of the eye. And there's even a commercial product that's sort of based on a similar technology called pin tilt. Another approach, again, very, very popular, and there are lots of designs in commercial use based around this, is to use folded optics, right? Generally, it's used to make the display more compact, but it can also be used to enhance the field of view. The work that I'm going to talk about sort of follows a different line of work that has to do with curving certain components, right? So you can imagine that when you're imaging a large field of view, if, for example, the display is planar, the tangents of these angles get involved, and tangent is kind of a nasty function as the angles increase. So if you can curve the optics or the display, then it gives you a lot of, the complexity of design can be simplified quite significantly. And the line of work that sort of hits upon this is this last one, what's called thin-VR. So here what they do is they take a cylindrical display, so take a display, curve it into a cylinder, and use a custom designed micro lens array that's also curved in sort of in the shape of a cylinder, with each micro lens set designed so that the display produces the light field that you would care for on the pupil. Okay, so if you take this idea and take it to its logical conclusion, perhaps one solution to consider is this. What if we had a perfectly symmetrical solution, right? So imagine that the eye looks at a spherical display with spherical optics in front, so that every axis, no matter where the eye looks at, the optical configuration is more or less the same. And if you did this, there's no off-axis settings, right? Everything is, if you can imagine one axis well, you can imagine the whole thing extremely well. Unfortunately, this particular idea doesn't work, simply because if you did the math, you would see that when you have these kind of dome lenses, they end up they have negative power. So all they will end up doing is moving your spherical display closer to the eye, which kind of beats the point. You could just put the spherical display closer to the eye in the first place and remove all the optics, right? So if you cannot do fully symmetric design, maybe the next best solution is to do partial symmetry, right? Partial rotational symmetry, or what we call n-fold rotational symmetry. So imagine a design where the optics repeats itself when you rotate the eye by certain amount. Right? So imagine the eye is somewhere, it rotates by some amount, few degrees, let's say 10 degrees, the same configuration repeats itself. So now a global design problem can be reduced into a local design problem. We need to effectively design one copy well, and then tile it again with using rotational symmetry, and that would naturally satisfy. We can extend it to arbitrary large field of view because of the rotation symmetry of the eye, rotational motion of the eye, and all of the nice things that the eye does for you. So we can now look at, therefore, 3D shapes that satisfy this rotational symmetry, this n-fold rotational symmetry, the fact that if I rotate the eye by some amount, the same shape will recur. And these shapes are called platonic solids, right? Something that's very well known for thousands of years. And there are 5 of them, each of them giving different amount of rotational symmetry, depending on the specific configuration of the shape that you're looking at. So we can now take these platonic solids and build an imaging system based around them. So a display system based around them. So we still retain the spherical display, but for the eyepiece, the outer surface of the eyepiece is made up of a sphere, and the inner surface that we carve out has the shape of a platonic solid. So effectively, we have two surfaces that have full rotational symmetry and one surface that has n-fold rotational symmetry. And the idea is that this will naturally can be naturally extended to be a very large field of view simply by tiling these planar facets as given by the specific platonic shape that we end up using. So the biggest advantage of this approach is that we only need to design and optimize or understand the performance of one planar facet, right? And it naturally extends for the entire field of view, right? So a good place to therefore start is to understand what happens to the foveal light rays. So imagine now that the eyeball is rotating, so the fovea is being dragged around, and we can take the rays that would fall on the fovea, the center of the fovea, and understand what happens to them as they fall on the spherical display. Okay? So you'll see that for the most part it forms a single spot, but whenever it hits the intersection between two planar facets, right, each of those lenses acts separately, diverts the two cones of light to different spots. So you end up with, effectively, if you look at the collection of all of these light rays, you end up with something like this, right? So each of these lenses is essentially a plano-convex lens. It forms a small image behind it. It's probably more easier to look at it what happens from the point of view of the display. If I now take a scene, a wide field of view scene, and I want to present to the eye, this is the pattern you'll end up showing on the display. So you can kind of see that this image is fragmented with the idea that each of these plano-convex lenses will bring back the fragments when your eye sees to it, at least if you look at only the foveal light rays. But we should also need to consider the light rays that are off the fovea, because those are light rays that still fall on the retina. And if you trace them out, you will immediately see that this simply falls if I hold the gaze fixed and look at what are all the light rays that come from different parts of the retina. If they lie on different parts with different amounts of blur, they still fall on the spherical display. And now if you look at the image that you have to show to satisfy the parafoveal regions, right, the regions outside the fovea, you end up with a much fuller display much fuller image on the spherical image, on the spherical display. And the idea is that everything that's in these blue circles corresponds to light rays that would have landed on the fovea, and the things outside of them are basically ones that will only be seen in the parafoveal region. And we can see the first sort of problem with an approach like this, right? There are going to be points on the spherical display which will map to which will map out to the eye at two completely different settings, right? So here the red bundle of rays are imaged on the parafoveal region when the eye is looking straight ahead, and at the same time it's also going to be imaged on the eye when the eye is looking along a different axis. So we call these pixels conflicted pixels, because the pixel on the spherical display has to satisfy two completely different constraints. So what controls these conflicted pixels? The sort of simple analysis shows that the angle between the planar facets, what we call the dihedral angle, controls the region of that where the conflicted pixels will occur, right? And as the angle decreases, as the planar facets become more acute in angle with respect to each other, the region that's devoted to the parafoveal region increases, which means you're going to have much fewer conflicted pixels, or the conflicted pixels are going to be pushed very far away from the fovea. All of it suggests that perhaps we should use these platonic solids which have very small dihedral angle. But the challenge with that is, as the dihedral angle increases, we have more planar segments, which means that the thickness of each of these plano-convex lenses is reduced, and we'll also probe them much closer to the optical axis of each, which means optical aberrations increase when we have smaller dihedral angles. And this we can capture by essentially simulating these and running them through MTF analysis. And what we end up seeing is that we at least need a dihedral angle of about 120 degrees before, so to match the foveal resolution of the eye. So what you have here are MTFs for different dihedral angles. Also shown is the retinal resolution based on a simple model of the retinal resolution. And at the foveal resolution, to even get some reasonable contrast, you need a dihedral angle that is at least 120 degrees. Things are a little better in the parafoveal region, in part because the eye's resolving power decreases much quickly than the optics, so things work out well. So, in a nutshell, we have this choice of inner surface in terms of platonic solids. At one end, we get few conflicted pixels, and the dihedral angle is very small. But it also means fewer facets, and which means you're going to have a lot worse optical resolution. And so, on the other end, we get that optical performance at the risk of having more conflicted pixels. And if you arrange the platonic solids in terms of their dihedral angle, something like the dodecahedron gives you a good trade-off between these two extremes. We can also look at a whole bunch of other shapes which are not platonic solids, but which are useful things to evaluate. Right? One of them is the soccer ball, a truncated icosahedron. Then we can also sample them. We can increase the amount of sampling by giving up n-fold symmetry just for sake of purpose of evaluation. Now, simulation results sort of confirm these theoretical sort of or these predictions from analysis. What we do observe is that when we use platonic solid which has a very small dihedral angle, we do lose foveal resolution. So here you're seeing an image rendered on the back hemisphere of the eyeball, and we lose resolution at the foveal region, which is the middle, which we gain very quickly as the dihedral angle increases. But you can now see that the parafoveal regions, the regions outside of the fovea, get all sorts of aberrations because of conflicted pixels. So here is a rendering as the eyeball rotates in the scene that I was showing you earlier. Maybe this is a better one, which is much more zoomed in. The fovea is right in the middle, a tiny circle of about a few degrees. So in the interest of time, let me quickly go through some of the results from a real prototype. So our display requires a spherical OLED display of some sort with an eyepiece that has a spherical outer surface and a platonic inner surface. Spherical displays are very hard to manufacture, in part because it's very hard to take a planar display. You can't take a planar display and fold it into a sphere. It's not possible. The best hope is an emerging technology in terms of stretchable OLEDs, which could potentially be shaped to this particular form. So this is one particular problem. The other problem is, what about the eyepiece? Designing lenses, again, is not something it's theoretically simple, practically extremely hard, right? What we ended up doing was, one of my kids bought a Christmas toy which had the shape that we wanted except for the platonic part. So I borrowed it from her to build a prototype out of this particular thing, and that prototype was this. And I said I did it, I meant my student Sagnik did it. So here's the result from this real prototype. This is showing a 40-degree cone of light. We use a cylindrical display, so it's really only the central line that you should care about, because our display doesn't curve in both axes, only curves along one particular axis. And a panorama that we stitched from that image that you saw with the input image that we should have obtained. Here is another more catchy video. If you look closely, and I'm happy to take this offline because I'm running out of time, you'll see there are lots of aberrations, especially in the off-axis region. Some of the Moiré effects you're seeing is simply because we are using a camera to capture this, so the sampling patterns interfere with each other. So in summary, what we have is sort of a simple design, conceptually simple design for building a wide field of view display that uses a spherical OLED display. There's a lot of challenges in fabricating these, and of course there are lots of challenges we still have to encounter with fabricating the eyepiece. But in a nutshell, that's PlatonicVR. Thank you.
Thank you very much. Are there any questions? Nothing? I think we're probably back on time, right? No hands? Okay, I think we use this to get back on time. Thank you. Okay, so the next presentation, while he sets up, is by Gordon Retzstein from Stanford University. I think associate professor? Yeah. Okay. Associate professor at Stanford University. The talk is titled Holographic Near Eye Displays. Thank you.
Thank you for the introduction, and thanks to the organizers for putting together a great conference and inviting me. The last few years, and that's holographic near displays. Stereoscopic displays have a long history, and when they're mounted close to the eye, we call them near-eye displays. They've been around for a while, actually stretching back longer than this history chart, and you've probably been playing around with a couple of these devices. Most of these displays are based on the magnifier principle. A lens magnifies the image of a small display mounted close to your eye to form a virtual image at a distance that is comfortable to accommodate at. This distance is given by the Gaussian thin lens equation that you can see here. But this design principle has two problems. First, you need a distance of about the focal length of the lens between that lens and the display panel, so that adds optical bulk and increases the form factor of the display. Second, the display shows you a 2D plane to each eye, which is very unlike the physical world where our eyes can accommodate at all different distances. In this case, the accommodation of each eye is fixed to that plane. This leads to discomfort and double vision caused by the divergence accommodation conflict. Today, I'd like to convince you that holography is a very promising platform to unlock a new generation of ultra-compact near-eye displays with high 3D image quality and large étendue. So before we dive into that, I'd like to take a step back and talk a little bit about what holograms are and why they are so challenging. You've probably seen holograms on your credit card or in other optically printed forms. These are typically thin chemicals that have an interference pattern of light recorded into them. So they're very thin, but they have the ability to create a lifelike three-dimensional image. The interference patterns recorded in these holograms typically have feature sizes that are on the order of tens of nanometers. So this is only a small fraction of the wavelength of visible light. And unfortunately, these patterns in optically recorded holograms cannot change. So we're looking at static holograms. We'd like to do this digitally and show moving pictures. So we need programmable phase or amplitude spatial light modulators, such as DLPs or liquid crystalline silicon, to show these holographic features. But the feature sizes of existing microdisplays are very large compared to the wavelength of light, actually multiple times that of the visible light. The problem with using large optical feature sizes is that the amount of diffraction angle that can be created really depends on the feature size directly. So if you have large pixels, you cannot diffract light efficiently. And that severely limits the usefulness of holographic displays in practice by affecting the field of view, eye box size, and other issues. So you need a small feature size compared to the wavelength of light that you're working with. Now, holographic displays are not new at all. They've been invented by Dennis Gabor in 1947, and he received a Nobel Prize for this in 1971. But traditionally, these setups have also been large. So if we want to make them useful for near-eye displays, we've got to make them small and lightweight. Moreover, the image quality that's experimentally been achieved, even until a few years ago, has been fairly poor. We've already seen this in a couple of talks today. There's speckle and other issues that are really difficult to get away. So image quality has been poor. In this talk, I'd like to tell you a little bit more about my group's efforts on achieving high-quality holography, building very compact holographic near-eye displays, and also about recent approaches to computer-generated holography algorithms that extend Gaussian splatting to the wave optics domain to make them directly compatible with holography. So let's start by discussing the image quality issue and how to solve it. The key takeaway message up front, you need to calibrate your display really well. So that seems obvious, but it's actually not trivial to do. Just so that we're on the same page, a holographic display or near-eye display typically comprises a coherent or partially coherent laser, some collimating optics, typically a spatial light modulator that modulates only the phase of the light in a per pixel programmable manner. And so the amount of phase delay that you create indirectly creates an image in front of the SLM. We can't see phase directly, so we need to form an image through diffraction and interference somewhere in a volume in front of the display. And then there's an eyepiece that magnifies this image. So the question really is, how do we compute a phase pattern that we can show on the SLM that creates a high quality image? And the challenge is that the image quality is low because there's a mismatch between the forward model that we use for simulation and for computing the pattern and that of the physical optical system. This is governed by optical aberrations, nonlinearities or non-idealities in the electronics and drivers of the SLM, interreflections, many other effects. It's very difficult to model them all accurately. So traditionally what people have been doing is taking Joe Goodman's textbook on Introduction to Fourier Optics and implementing the forward model out of that. So that would typically include things like the lookup table or the electron to phase conversion of the SLM. We're modeling the field on the SLM with amplitude and phase. We're then propagating this field in free space, for example, using the angular spectrum method. And that gives us a target field at various distances, because the free space propagation operator depends on the distance, and we can simulate what the hologram would look like at different distances. The way we try to address this image quality issue in calibrating the display is to come up with a parameterized version of this model, because it typically doesn't model the physical optical setup well. So what we do is we introduced neural networks or learnable parameters, let's say, that change the field incident on the SLM or that leaving the SLM. The free space propagation operator we can still use, so think about this as a residual neural network that only models the difference between the simulated model and the physical optical setup. But then we also learn the lookup table of the SLM and a couple of other physically interpretable parameters. We follow the standard neural network training paradigm by capturing a lot of pairs of phase patterns and intensity images that we can capture with the camera once in a pre-processing step with the camera focused at different distances. And then we train this model in a pre-processing step. Interestingly, if you look at the learnable parameters, for example, on the SLM or in the Fourier plane on the bottom, if I show you how they actually converge to physically meaningful results. So for example, on the bottom, you see the amplitude in the Fourier plane learns the aperture stop that we put into the physical setup. So that's encouraging. And the image quality is significantly improved. For example, here's a setup that I think Evan built back in his day in my lab, and the image quality is okay, but there's a lot of speckle. So this is a single frame of a hologram using just the angular spectrum method. If we use a calibrated model, account for the quantization of the phase SLM, and also use time multiplexing, we can significantly improve the experimental image quality. So this is encouraging, and back in 2020, we had our first paper called Neural Holography on this line of work, and the image quality was significantly improved. We can show videos, these are offline captured, so they're not captured live, but we can get experimentally captured image quality that is getting close to what you would see with a conventional OLED or some kind of an amplitude display. This is in 3D, we can refocus the camera back and forth. Just to convince you that these are not simulated results, we're just showing an uncropped version so you can actually see all the stray light outside the SLM. We're refocusing the camera back and forth. So it's starting to look pretty good, but the real magic of a hologram is that the pattern that you show on the display, as seen on the left, it doesn't really resemble the image that you see. This is the phase delay on the left, and on the right you get a full 3D volume from that single phase pattern or a time multiplex phase pattern. There's some, I think, compression artifacts in these videos, so I apologize for that. But this is sort of what the hologram actually looks like on the left. So here's again a zoomed in version of the experimentally captured results. These are 2022 papers. And you can see the time multiplex pattern. We actually saw this earlier from another really good talk, where time multiplexing really helps remove some of these artifacts and speckle. So we just slowed down the process here. We showed all of this 2 years ago at SIGGRAPH in the emerging technologies section. So these systems actually work and people seem to like them, but we still have a long way to go to actually make them practical. So here's some results captured with just a cell phone from our eTech demo. All right, so I think we've made a lot of progress on calibrating the displays and achieving reasonable quality. There's still a little bit of ways to go, but there are more challenging problems to be solved also with these types of displays. For example, we need to make them small. The form factor is a major hindrance if you are thinking about near-eye displays for VR or AR. So again, I'll give you the key insight that allowed us to develop these ultra-compact displays up front. The key insight is that with a hologram or a phase-only spatial light modulator, you can actually correct optical aberrations of the light propagating through a waveguide or imperfect optics. So we can build imperfect optics and correct for the imperfections using the hologram itself, and that's something you simply cannot do with any amplitude display. So holographic displays enable unique degrees of freedom that you can't get any other way. So again, just looking at a photo of a VR headset today, you will see that there's some bulk, and that's mainly just air, because you have this distance, which is about the focal length of the lens, between the eyepiece and the display panel. So a couple of years ago, we started looking into waveguides and designing them for holographic displays in particular, and our goal was, again, to create compact, 3D, high-quality images. Waveguides are not a new technology. They've been around for a while as well. But typically in a waveguide, which is used to build a pair of glasses, you have a small projector that's embedded in the frames. They project an image that's coupled into the waveguide. There's total internal reflection bouncing the light to an outcoupler, and that directs the light to your eye. These waveguides are still not perfect because they can only show 2D images because they need optically perfect systems, and they have a projector that require, again, some bulk. So we thought maybe we can design something that uses the unique abilities of hologram to create 3D images in a smaller form factor. To design a waveguide for 3D holograms, you basically have to do the whole thing from scratch, which is not trivial. So first we designed this waveguide and the geometry of the waveguide and the couplers for 3 wavelengths, 3 visible, so RGB, so that they overlap, because they all have different dispersion angles. Then we inverse designed meta-surface elements, so these are nanophotonic elements that will couple the light in and out of the waveguide very efficiently, so doing this efficiently is hard. And we did that using basically an inverse design paradigm, so inverting Maxwell's equations to optimize the design shape. And then we fabricated these meta-surfaces on a waveguide, and they look kind of like this. The system itself looks sort of like a pair of eyeglasses, and we have a commercial SLM in there. The setup used to capture the results you can see on the right. And then if you look at the images with a conventional wave propagation model on the left, and those using our learned wave propagation model that I alluded to in the earlier part of the talk, you can see pretty good image quality. So it's getting there. And this is an optical see-through AR display, I should mention. In this case, I'm only showing VR type results. But the image quality is getting there. Now, one challenge with this project that we published in Nature last year was that the étendue of the system was sort of limited. Étendue is the product of field of view and eye box. Typically, you want a large field of view, as Aswin just convinced us is really important, but you also want a large eye box. So that's the area within which the pupil can move. But it's really hard to get that. You can trade these two off for one another. So you can get a larger field of view, but it comes at the cost of a smaller eye box. And so in our recent project, that's going to be published in Nature Photonics any day now, we designed a really compact 3mm display that has a very large étendue. It uses a MEMS scanner to individually scan out different parts of the pupil, and a phase SLM to create the image in each of these subpupils. We call it synthetic aperture holographic displays. It looks like this in practice. And the image quality that we can achieve using a new calibration method, that's an advanced version of what I showed you earlier, looks decent. The eye box is very large. You can move the camera quite a bit, and you can refocus to different distances with appreciable effects. All right. So I just want to allude to a new project that we were working on pretty recently, where we thought about, well, how do you actually take the content that you want to show on a display and create the hologram? That's typically called a computer-generated holography algorithm. And there are many different ways of computing holograms. You can use point cloud representations, for example, to do that, or polygons. You can use image layers, RGBD, or light fields. But we chose to go down the route of building on recent neural rendering techniques, specifically Gaussian splatting. So if you haven't heard of Gaussian splatting, it's a method that takes a couple of input images, distills them into a set of 3D Gaussians, and then you can render these Gaussians from novel perspectives, so views that you haven't seen in the input images. So that's what Gaussians are typically used for. And so what we worked on is a project called Gaussian wave splatting, where we extended these methods to connect them to wave optics theory and enable efficient holographic displays with them. So we take Gaussians that are representing the 3D scene, that are pre-optimized, and it actually turns out that the Fourier transform of a Gaussian is also Gaussian, so there are very efficient ways to doing all these holographic calculations based on Gaussians. The hard part is then to figure out how do you take all these Gaussians representing a 3D scenes and splatting them together while maintaining occlusion effects and view-dependent effects and things like that. So I'll defer to the paper for technical details on how we did that. But the experimental results look pretty promising. Point-based methods typically have holes. Polygon-based methods have a lot of issues, and these Gaussian wave splatting-based, this approach is looking a lot better. I'll just show you some results before wrapping up. Here's the camera refocusing to different distances. You might have seen this loader scene from the Nerf paper originally. Here's another garden scene. So these are all experimentally captured results, so they're not going to be perfect. All right, so hopefully I convinced you that holographic displays have made a lot of progress on both image quality and also compactness. One good thing is that SLMs are making a lot of progress. For example, a startup called Swave is building spatial light modulators with very small pixel pitches, so we might actually see very small SLMs soon. And with that, I'd like to wrap up and just mention that our lab is working on a couple of different technologies related to AR and VR, including eye tracking, perceptually driven rendering, micro-LED light engines, and other things. We're also working on neural rendering, scientific imaging, computational optics and imaging. So all the things that this community is excited about. So thanks to my collaborators and the group. And with that, I'd like to thank you all for attending.
Thank you very much. I'm looking forward to using that thin holographic display now, if you... Yeah, so are there any questions from the audience? Like over there.
Thank you very much. People talk about metrics like diffraction efficiency, reconstruction errors, things like that. Can you give us some numbers there?
So diffraction efficiency is something that is inherent to the hardware. So I would say we've been mainly focusing on pushing the software aspects of holographic displays and some of the compactness. I'd say efficiency on the waveguides, I think is in the 80s, 80% or so, like 80s. So with many bounces, you're going to get less light, obviously, right? The diffraction efficiency of these SLMs is also on that order, I would say. But again, we're using commercial SLMs. I think we're closely approaching the limits of what we can achieve in software, and we really need some advances on the hardware also, which the SLM is a big part of. I don't think you're going to see a lot of improvements on the sources. So we'd like to work with laser diodes ideally, but then the challenge is also that they're partially coherent, and we need to calibrate that, which we can do also. Actually, I skimmed these details, but I think the SLMs are one of the key technologies that need to advance.